So, the two main avenues of what can be called game theory is game theory per se, which is analysis of behavior in a given interaction, which we are going even to do in some examples today, and mechanism design and implementation theory, which are in a way the opposite, the dual question. So which condition shall we create to motivate some behavior? So we need to not like that we have an interaction and the question is what are the players going to do, but rather we know what we want them to do, and the question is which interaction shall we design in order to motivate them to do that. So there are many questions like which condition will motivate some desired behavior, on which behavior is both desired and can be motivated, and what can be. Sometimes the question is, especially in implementation theory, what are the behaviors which behaviors can be motivated at all, because maybe not everything can be motivated, or maybe what we want can be motivated, like people telling the truth on the voting ballot, but also telling some kind of a lie is also beneficial. So those conditions, which interactions shall we design in order to get something, that's mechanism design and implementation theory. And we are going to deal with game theory per se. Probably, maybe a little bit. We're going to graze about on the topic of mechanism design a bit next lecture, but I don't think we're going to dive deeper in that topic unless you have time. So the game theory branch is can be non-cooperative or cooperative. These are the main directions, and we're mainly going to go into non-cooperative game theory, and they differ by modeling approach. So non-cooperative game theory looks at models where you have some players and they have some possible strategies. So a model can have any individual strategies as the model offenses. Now, cooperative game theory, on the other hand, studies possible coalitions. So it's not like a player chooses a strategy. No, a player chooses which coalition he joins or which coalition she joins, for example. So you already model things in terms of coalitions. As we guess, that's as we can guess, hope, that's something which is related to political and sometimes business capital. So we are not going to deal with cooperative game theory much. So mostly we are going to talk about non-cooperative game theory. The most maybe simple, but I'm not sure that's the simplest. Anyway, we are going to mostly work with non-cooperative game theory, at least in the beginning, and that non-cooperative game theory in turn can use either dynamic or static game. So dynamic models actually the process of play. So let's say in the Caribbean crisis, an example we will see today. So the US and the USSR, US can deploy that, USSR can deploy that, react, not react. You really model every move. In the case of modeling chess, you model what each player does at his turn. And the static model on the other hand, model strategies abstractly. So of course we don't say strategies doesn't have any ingredients, no, but simply we look only at the strategy as that strategy A, the strategy B, and that's what the utility that the player derives from that strategy if the other player does that. Now, we will see. What I mean is that it's only a static view on the strategy. And now, static is a bit simpler, and we're going to work with mostly static, but not only. Classes of non-cooperative games, with which we will work less, if at all, but still. And we also, non-cooperative games we are going to. So classes of non-cooperative games, those are games which we are going to work with, can be also classified by many parameters. For example, by the utilities. So if a game can be seen, of course, now I'm hand waving a bit, but just we will of course define exactly what we mean when we need that. But now I'm hand waving, so the games can be potential, zero sum, and so on, in the sense of the utility. So a potential game is a game where what each player wants can be seen through what all the players want can be seen as maximizing some common potential function. So there is a certain kind of coordination between the players. That coordination can be modeled as a potential function. The other extreme is actually when there is a total miscoordination. So when the interests of the players are exactly the opposite, the game is called zero sum. So there is one pie which they need to divide between them, and whatever I get is what my opponents, usually we talk about two players zero sum, it can be more, whatever they lose. So the sum of what we get is the same. It's zero or constant in general. So potential games are about some kind of coordination between what they want, and zero sum is when they are also coordinated, but the interests are exactly the opposite. Of course, the typical game can be both. So they have some, they sometimes can be helpful to one another, sometimes they destroy to one another. And now the other another parameter by which we can classify non-cooperative games is the strategy set the games have. So what the players can do, and if all the strategy sets are finite, so excuse me, all the players have only finite number of possible actions, and what I call strategies. Let's say strategies. And then the game is called finite. Otherwise, the game is called not finite. The number of players, we're going to assume it's always finite. We can look at, there are games which are not not a finite number of players, but unless I tell you otherwise, we assume the number of players is finite, and the question is whether the strategy is. So the routing game can be seen as a game of infinite number of players. So usually the game is not seen as a game in general. So, well, when we need, we'll see when we cross. So by the ability to win, the question is, does there exist a strategy for one of the players such that that player, regardless what the other player does, that player always can win? If you have a game where exactly one person always wins in any single play, in any instance of the game which is played, exactly one person wins. It's still a question whether there exists a strategy for one of the people which allows that person to always win. That's not the same as any play ends with someone winning. And in a finite game, when you have so-called perfect information, that's true, that's the case. But when the game is infinite, that's a very deep question. And actually, there is an axiom which is called the determinacy axiom, which is definitely beyond our scope, but I'm just telling you that there is such a thing. Which, if I'm not mistaken, it contradicts the axiom of choice. So if you see the axiom of choice, then you can prove the determinacy axiom does not hold, which means that there are infinite games where no player can have such a winning strategy. But that's definitely all those infinite games. And these are about dynamic games where you have those actions, and the question is how to act. These are all way beyond our course. I just want to tell you that there are questions in game theory, practical area as it is, which are really deep, and they can be not proven, and I think there is a proof that can be neither be proven nor refuted, but that's definitely beyond our topic. If someone, by the way, wants think about infinite games and about that topic, I recommend you to watch the lectures by Joel Hampkins. He works in logic and also in infinite games. And you can look him up on YouTube, for example. So the cooperative games, which we are probably not going to deal, or not much, but still, those are games which just model the value of each coalition. It's called there is a characteristic function. So which coalition this function determines the value. If that is the party that you have, or that is the industrial organization that you form, that's what you are able to obtain, political, economical, and so on. You can also express this value in different manners, and there are many ongoing studies on that. And classes of cooperative games also can be defined, first of all, by the possibility to divide the coalition value. So if a coalition is able to achieve something, let's say you form a cartel and you gain some extra money because of the cartel. So the question is, can you divide that money? Apparently you can, if it's about money. So can you divide the coalition value? Anyhow, if yes, then it's called transferable utility. A game with transferable utility. If you cannot divide the coalition value in any possible manner, so there are only prescribed ways to divide the value, then it's called a game with non-transferable utility. Another way to classify those cooperative games is by the value function. You define the value of a coalition by a characteristic function, and the function can be corresponding with the game can be sub-additive, super-additive, or neither. But again, this is just for general knowledge, so it's important to have it too. And now let's talk about the dual thing a bit. So mechanism design and implementation theory, and remind you that's basically a dual area to game theory, which is often seen as under the same umbrella, but it's a dual area in the sense that it asks which rules shall we design in order to get something. For example, which auction shall we have for eBay to work as we want it to work? So mechanism design looks at the rules in order to which are needed to motivate certain behavior, such as honest bidding in an action, voting without actually without not without imprecise voting. So when you don't have any motivation to manipulate, distort what you actually want. And often we want, for example, in the auction, very classical and very successful avenue, where there are many theoretical work. It's one of the avenues which definitely is practically useful. So there is the honest. You want to make the players, the bidders, bid honestly, and also want to sell the auction item to the person who values the most when you don't know what are their private valuations. You just assume that they behave rationally. The implementation theory is a bit similar, but it's less practical, it's more theoretical. It actually studies which rules can motivate some behavior you want, but usually it looks at all the possible functions which can be implemented. So all the possible behaviors which can be, let's say, equilibria, Nash equilibria under those rules. Mechanism design, it's enough that you just make some behavior an equilibrium or weakly dominant, and I don't say what it means yet, but I'm just giving you an impression of what that is. It's enough that you just make some behavior profitable for rational players, whereas implementation theory ask about what are all the possible things which we might motivate. It's a more theoretical domain, though it also, of course, has its uses. And possible applications, so there are many of them, but let's just mention a couple or a bit more. So non-cooperative game theory definitely can be applied to war, to economical things like investments or investments of times. And let's say my PhD piece was about investments of time and other efforts, not other resources, not necessarily economical. Production, evolution, so biology. Minor Smith, if you read the book by The Selfish Gene by Dawkins, which I definitely recommend, Minor Smith was a very famous biologist. I think he got a Nobel Prize, and he definitely was one of the pioneers of using game theory to biology. So definitely game theory found its use in biology, and you can even say that it's a bit related to mathematical biology, because there is this topic of computational biology. You can speak about game theoretical biology. And cooperative game theory naturally works well. It's well suited for political game and all those divisions of cost and profit. Sometimes you just need to decide how shall we divide our costs when we use something together. How shall we divide the cost of building a road? Because not everyone necessarily uses the road to the same extent. But if we divide it somehow, maybe some people would want to participate in that. So that's an important question. And mechanism design, of course, is used in those questions of preference aggregation, and you need to make a decision based on several decisions of some players who may be strategic. For example, voting. That's maybe probably the most famous example of aggregating preference. Legislation, so you want to ask which laws will make people do what you want. So sometimes you just want, for example, when the laws were like naive, and you see that if you make a law, for example, I think the Russian guy, what's his name? Savatiev gave this example that probably he might have taken that from someone else, that if the government wants to leave more money from the population, it often makes okay, those who earn more money should pay me more. And even if you forget the moral question whether it's fine to just take money from people simply because they have earned some more money than others, it can be sometimes impractical, because that can actually motivate people to earn less money. And sometimes the taxation schemes are really stupid. Like, if you earn less than $1 million, you pay this percentage. If you earn more, you pay a higher percentage for all the sum. Of course, if you have such a taxation system, people usually don't. But if you do, that's really stupid, because then, of course, you can earn a bit more, and your net will be strictly less than when you used to earn less money. So it's important to think how people behave when you make laws, and here definitely you need to take into account that people are boundedly rational, and that's definitely a very important area which I believe is not yet studied enough. It's definitely an under-researched topic. And of course, auctions, which is being researched all the time. Also, how you can encourage some norms in society. So, for example, if you want people to drive nicely, and you want them to use the resources of whatever, the road, only if they really need that and all that. So how can you encourage such norms? So there are many important applications, and of course we are going to, in this course, look at take a normative approach. So we define that's how people behave, that's a norm. Under those assumptions, what happens? What actually happens, the descriptive view will inspire definitions, but that's not what we are going to work on per se. And what we're going to do is mostly using the linear utility or the expected utility theory of von Neumann and Morgenstern, So those guys also set the basic utility theory, which is known to be not exact as many trust works are. Definitely has been improved, and it is being improved as we speak. The question how people behave, what people actually want, is definitely hard, but that is still the most important because it's so natural and so amenable for interaction, for analysis. That's the most important model, at least for us. So that's basically one of the pillars of game theory, utility theory. The notion of what people want, that's what the utility theory is about. And as I said, we are going to employ the standard model of von Neumann Morgenstern. And there were, in the 60s and 70s, anyhow, there were many famous examples where people definitely are not rational and in their preferences are not what we now will define as natural. So people are not as easy to analyze as we wanted. The most famous paradoxes are by Allais and by Ellsberg. But it's still important. Now, following those experiments by Allais and Ellsberg, one of those guys also was famous with publishing those Pentagon papers, I believe, about which caused a huge political scandal in the US. I don't exactly remember the details, but if you are interested in history of politics, you may look up two of those names and look up who's famous for some political discovery. And anyway, so this theory we are going to study was substituted by the famous prospect theory of Kahneman and Tversky. For a layman introduction, you're welcome to see the famous book by Kahneman, which is called Thinking Fast and Slow. It also gives a lot of much other material. But still, it's important. So now let's define the theory. A lottery is a distribution over some outcome. So we can have this, and this outcome. And the lottery is a set of outcomes with the probability with which each outcome is played out. So a lottery I can be written simply as a linear combination of outcomes OI, where PI is the probability of outcome OI. The probability is all non-negative, and their sum is 1. So we are sure that exactly one of those mutually exclusive outcomes happens. And I is this combination. That's a general model of something which a game can result in. So it's a linear combination of sure things. So you can either, for example, like in those examples of Allais and Ellsberg, which we are not looking at here, but there was something like you either get $100 with 100% probability, or you get 1,000 with 10% probability. So, and for example, each one of those is a lottery, or you get $100 with another lottery with 70% probability and $1 million with 30% probability. That's also a lottery. And we denote preferences by those curling smaller or greater or the same or at least at most or at least signs. And there is this famous theorem, which is the basic theory of utility theory, which basically tells which assumptions we need to make in order to be able to express the preferences by simply a numerical function. And we are going to always, unless said otherwise, assume that. So we are not going to prove the theorem, we are just going to always assume that the theorem holds, but we just need to know what the theorem is about. So you are welcome to look at the Stanford Encyclopedia of Philosophy online It's really a nice place, and you're welcome to read about it a bit more. But basically, the theorem says as follows. So consider a finite set of outcomes. We're going to assume, by the way, that for any set of outcomes, even infinite, it has this, unless said otherwise. But the theorem is, in this simple version, is a finite set of outcomes and preferences over the set of lotteries L. So the preferences are over the set of lotteries, which are distributions of outcomes. So you are told what the players prefer from different distributions of outcomes. It's important. You're not only told that, for example, a player prefers money as more as possible, which is often the case, usually the case, but you're also told that if you give me that much with that probability and that much with that probability, and then I prefer that to some other team, like this much with this probability and this much with that probability. So you are given the distribution over lotteries. And the distribution is closed under mixing probability. What it means that for any probability P, for any number P between 0 and 1, and for any two lotteries, getting the lottery P with probability L, actually getting the lottery L1 with probability P, and the lottery L2 otherwise, is also in L. That's what it means. It's closed under mixing. We are not telling yet how much the players will want that thing, but it's in L. And we are given preferences over all this set L. Now we assume that we can reduce those lotteries in the following sense. For any P and for any set of probabilities Pi, the total sum of which is 1, and Qi, the total sum of which is also 1. If you look at that combination of Li's with Pi, and you take this combination, this lottery, you know that it's a lottery, right? Because all the combinations of lotteries are lottery. If you look at that one, you take that one with probability P, and some combination of Li's, other, with weights Qi, with the rest, and that's also, now that's in turn also a lottery because that's a combination of y. So combination of PILI is a lottery. This is combination of lotteries. Finite combination of lotteries. Combination of QL, combination of PILI. I think I've mouse slip, so it's not. I cannot draw properly in. Combination of PILI is a lottery. By induction, any finite combination of lottery is a lottery. Combination of QLI is also a lottery. Their combination now is also a lottery. And it's the same from the point of view of players, of the players. Of those preferences. As if you just open the parentheses and look at the combination of P times Pi plus 1 minus P times Qi of Li. So if you open those parentheses, that's the same. It's intuitive. If a player is linear with respect to the preferences, which is actually not the case, of course, with real people. But if people were really mathematically simple, that's what would be. Basically, those assumptions are what you would want people to be. And then the preferences satisfy the axioms. Now they're going to have yet another set of axioms which are natural. If and only if there is a function, a utility function, from the options, from the outcomes to the real numbers, such that one lottery is preferred to another lottery if and only if the utility combination of that one is at least as large as the utility combination of the other one. So in other words, the preference satisfies those axioms. We are now going to look at detail natural axioms, even only if they can be represented as a utility function. As I said, we always assume those things all hold, unless said otherwise. And such utility, when it exists, is unique after a positive linear transformation. So if there are two utility functions which fulfill that, that means that one of them is the other one times some constant plus a constant. I think that's in a affine transformation, but I think that's what I mean. Yeah. I think that's what I mean, because if you can always add a constant. Okay, so completeness. Now, what are the axioms? And let's just go over that. So it's completeness. Every two outcomes are either such that one is preferred to the other one or the other way around. The preference relation is complete. Transitivity, so if 2 is preferred to 1 and 3 is preferred to 2, then 3 is preferred to 1. Continuity, if you have 3 lotteries, such that 3 is preferred to 2 and 2 is preferred to 1, and you can represent the one which is in between as a linear combination of those two on the edges. And independence. There was no space, so I've written independent. It's independence. So if L1 is worse than L2, or at least as good as at most as good as L2, then for any P between 0 and 1 and for any L3, combining this PL1 with L3 is at most as good as combining PL2 with L3. Because L1 is at most as good as L2. So it doesn't matter what you add. If you start with that, you add and with that. Okay, so those are natural assumptions, and we assume those hold. And okay, as I have said, people are not so nice, not so, or maybe they're nice, but they're not that linear. So that's not really the case. It's not always, but that's good enough for many economical game theory purposes. Especially game theoretical, because economists really prefer now to look at more practical or more realistic functions. But even the Homo economicus, some of who's like that, linear, even that is not easy to analyze. Okay. So as I've said, unless we've said otherwise, we're going to assume the existence of such a utility function, and also that everyone is infinitely rational, so everyone does whatever is in his or her power to maximize according to her utility. The utility may be like stupid from our point of view, but the utility function fulfills those axioms, and the people are infinitely rational. In reality, sometimes you can be shown that people are not infinitely rational. That's not surprising. But the most surprising thing, even the utility function is often it's not fulfilling any axiom. So it's not fulfilling such axiom. So their preferences themselves are not natural, let alone that people don't maximize them. But that's what I assume, unless otherwise. And yeah, I have said it's not exactly I say and then I read. So that's not exactly what you have in reality. But that's definitely probably the most widely used assumption. That's definitely the first thing to do, and that's deep enough to definitely give us a lot of interesting, useful, sometimes counterintuitive results. So we'll concentrate on the non-cooperative game theory for now, for some time, and the model here includes players or agents who freely, I prefer the word players, but you may use any word you want, freely choosing strategies in order to maximize their own utility. The game here, so models that you have some participants who have some strategic interested parties, have some behavioral options, and they behave in some way. Based on the behavior, there are possible outcomes. And we also are going to look exactly at what other utilities the players get from those outcomes. Also, we want to look at the possible outcome as a separate entity. So simply, if players behave in that way, if that is the profile of the strategies they choose, that's the utility. We want to really define an outcome of an independent notion. I'll now go to the exact model, so you will see. Yeah. You won't have to suffer the hand waving. We are now approaching the end of the hand waving and getting into the real definitions. That's going to be, I hope, really clear. So an instance of a play in a game is called a play. So a game is a set of rules. Players, rules, what they can do and what they get from them. A play, that's exactly what they choose. If you have a tree and a game tree, then exactly what they choose at each stage. At this concrete interaction. At the next interaction, they may choose something else. But a concrete instance of playing a game is called the play. That's simply an important thing to notice. That's the terminology we have. And the main models here are normal game. In other words, it's called sometimes strategic form game. We only look at the strategies abstractly. And extensive form, when you look at exactly what the components of the actions of each player are. Okay, so finally we get to the definition of the game. So finally we are past the introduction, in the introductory part of the introduction, and now we get into the core definition of the code, definitions of the code.